And now the question is the following. Do these semicircles here cover the entire inner area of the quadrilateral? Let's say you have a quadrilateral, just a random one, ABCD, and you take the sides as diameters of circles. And you take the semicircles that are built right on top. And now the question is the following. Do these semicircles here cover the entire inner area of the quadrilateral? Now, we don't know whether these semicircles here cover the entire area. So let's assume that you have actually a point here, let's call the point P, that is actually outside of all these semicircles. Now, before we move on, there's an interesting property that I would like to remind us all. If you have a circle, this is the center, you have a diameter, and all the points on the circles, when you connect them with these two sides of opposing, diametrically opposing, have here a 90 degrees angle. That is pi over 2. Let's put it 90 degrees. So no matter where you choose this point. Also, another interesting property is if you choose a point outside of the circle, like this, it's guaranteed to have this angle here smaller than 90 degrees. Now, this is an interesting property that we want to use in our proof. When we take PA, PB, BC, and PD, we can see that P is outside of this semicircle. So it means that the angle APB is smaller than 90 degrees. That is per this interesting property we have just seen right here. In a similar way, because this point P is outside of the semicircle, it means that the angle BPC is also smaller than 90 degrees. In a similar way, the angle CPD is smaller than 90 degrees because P is outside of the semicircle, and also the angle APD is smaller than 90 degrees. When we draw the line, we have here the sum of all the angles around P point is smaller than 360 degrees. That is 90 plus 90 plus 90 plus 94 times. And this is quite interesting because when you have a point P, the sum of all the angles around it is exactly 360. And we assume that there is actually a point P which satisfies this property, that it lies outside of all these semicircles. And the conclusion is that the sum of all the angles around it has to be smaller than 360. So that means that our hypothesis that there is such a P point outside of absolutely all the semicircles is false.